Hello everyone, this is the second part of your online lecture regarding columns. In the previous lecture, we discussed how a column with a buckle, so for example, we have this column right here, and let's say it's pin connected, we apply a load along the length of our beam or column, and it could buckle this way. Now, we also discussed about the effective length. The effective length depends on the type of connections at the ends of our columns. In this case, our effective length is equal to the length of our column. Now, what if we have different types of connections? So I'm just going to slice here. So we discussed this one, we discussed this one, we discussed this one as well. So let's say we have different types of connections. So we have A, B, C, and D. So we have different effective lengths. It depends on our support reactions. So let's say we have a fixed end, point B right here. We have free end A. We have effective length, which is 2L. If we have both pins, and this was our example during the previous lecture. So we have effective length is equal to the actual length of our column. Now we can also have one fixed end, which is B, one pin end at A. And if we have those connections, we have effective length is equal to 0.7L. And if we have fixed length for A and B, we have effective length of 0.5. What's the essence of those effective lengths? If we're going to go back to these equations here, so we have PCR is equal to pi squared EI divided by LE raised to 2. So the previous equation that we used for pin-ended connections, we only use L. But in this case, we can change L to L sub E, and everything would be the same except that we have to change LE. It depends on the type of our connections. And same thing for our stress, which is critical stress to buckle. So we have pi squared E, LE divided by R, that's radius of gyration, squared. So again, we just change LE right here. It depends on our connections. And these are the values right here. So this slide is important for you to solve such problems related to columns. Now, the problem for columns is, let's say, I'm going to drag my board here. So in all our example or discussion, we assume that, let's say, if we have a column here, our assumption is that our load P is exactly at the center of our column. Okay, so which is P right here. Now, what if, so let's call it point A and point B. What if we have this specific case? So wherein our load is not exactly in the center of our column. So let's say we have P right here, and let's call this one as E. So that's the distance from the this point up to the center part of your column. And then we have another P right here. So how can we solve such a problem? So it's called eccentric loading, and the secant formula topic in your book. Now, let's look at this specific case. So we have point A and point B. Now, we discussed about force couple system. And what do we mean by force couple system? So in force couple system, we can move this force right here. We can move this force into this spot right here. However, we also have to account the moment that it produces once we move that force from this point up to this point. So if we're going to move P, I'm just going to right there. So let's say it's our new column. So now we can move P in the center. So from this point the new location right now is this P right here. However, take note that once we move a force from one point to another, we are also producing a moment. So in this case, we produced a moment which we can call M sub A. And that's equal to P times E. And why it's called P times E? Again, this is E right here. And then this is our original P. We move our P to this spot right here. Oops, sorry. Okay. So now we already moved our P, and then we have another P right here. So basically that's our beam. Now, how can we develop equations related to eccentric loading? Just going to move the slides here so that you can see these forces here. I'm just going to drag back my whiteboard. So now let's imagine that we have this specific scenario right here, which is on the right side. Now we have P, we have another P. So let's say we cut our beam at this point, and let's call it Q. This is Q, that's A, and then that's point B. Now once we cut our beam in this spot, now you'd imagine that this beam right here would look something like this, which is the same on the right side right here. So this is Q, and this is point A. Now your point A has P. It also has a moment, which we call M sub A. And then we have shear, V, and then we have moment M. Now, based on these forces, we can develop our equation for our moment. And how can we develop those equations? So imagine we can sum the forces along Q. So some moments along Q. That should be moment, not forces. So moments at point Q, and then we can get our equation for M. Now, if we're going to sum those forces, we're going to get the following. So we have M is equal to negative Py. What do you mean by negative Py? Again, this is at this spot, this is at the spot, you have Y right there. And if you look at the right side, that's this Y right here. So your P produces a moment from point Q. So Q, and then going to point A, you have a distance Y, then you have a force P, so it creates a moment. In this case, we called it as negative Py. And then we have another term, which is M sub A. And we know that our M sub A, which is this guy right here, is equal to your P times E. Now, if we do that, if we substitute those numbers, we're going to get, just drag it here, M is equal to negative Py minus Pe. So that's the equation for our moment. Now, once we have equation for our moment, again, we can use our second order differential equation, which means I could have this expression here, b squared y bx squared is equal to m over ei, and that's equal to negative p over ei times y minus p e, and that's divided by e I. So we have the following equations. Now again, in order to solve this problem, because you have your d squared y right here, you have your y right there, similar to previous lecture, we're going to set p Let's call it small p. I think I forgot to mention in the previous lecture that it's small p. So p squared is equal to p over ei. And that will simplify our equation in order to get a solution to our differential equation. And if we substitute this assumption right here, we can get d squared y over dx squared plus, so we substitute it to the other side, p squared, so that's related to this one, p squared y is equal to negative, so we have another p over ei right there, so negative p squared e. Now we have y, we have d squared y. If you go back to your basic math, you will see that this is linear non-homogeneous. It's linear non-homogeneous differential equation, and of the second order with constant coefficients. Now, we're not going to discuss the details of this calculation, but the solution that you will get is somewhat similar to the previous one that we discussed in the previous lecture. So the solution for this differential equation is the following. So what you will get here is y is equal to a sine small p x plus b cosine small p x minus e. Now we have these equations here. We can use boundary conditions to solve our solution equation. So using boundary condition 1, so let's say we can say that at x is equal to 0. So let's assume at a that's equal to 0, we have y is equal to 0. Now using this boundary condition, substituting it right here, you will get the constant b would be equal to e. So let's call it boundary condition 1. Now let's move to boundary condition number 2. At x is equal to L, we have y is equal to 0. Now based on this equation, once we substitute it back right here, and let's call it equation 1 so that we can always go back there. Equation 1, we substitute it to equation 1, and then we will get the following equation. So using boundary condition 2, we're going to get a sine small p L is equal to e 1 minus cosine small p over L. Now, in order to get our equation, we can work around, or we can use some trigonometric identities in order to simplify these numbers right here. So using trigonometric identities, so just going to write the identities that we're going to use. Metric identities. So we're going to use the following. So we have sine theta is equal to sine theta over 2 cosine theta over 2, and let's call it equation number 2. So that's our first trigonometric identity. And you can easily imagine that this sine theta right here, we can substitute it for this equation. Now we can also use a second trigonometric identity, which is 1 minus cosine of theta is equal to 2 sine square theta divided by 2, and let's call that equation number 3. Now using equation 2 and 3, so I need to go back here, using 2 and 3. So again, note that this is 1 minus cosine, and if you go back here, that's 1 minus cosine for that equation. Now, if we're going to substitute this trigonometric identities to our equation, what we will get is the following. So a2 sine small pl, 2, we have cosine small pl over 2 is equal to 2e sine square pl over 2. And then eventually you can simplify the equation. So if you're going to check this equation right here, this one would cancel out here, and then this is going to cancel out as well. Sine, this becomes just sine, not sine squared, and eventually you will get this equation here. A is equal to E tangent small p L divided by 2. Now we have values for, let's call it blue. So we have values for A, we have value for our B, and we can now go back to our original equation and substitute those numbers. So what do we mean by original equation? We can substitute this one to equation number 1, this one to equation 1 as well, and then we're going to get the following. So substituting A and B, so A and B that we got, we substituted to equation 1, we have y is equal to E times, so I'm going to show you the simplified form, tangent small pl over 2 sine px plus cosine small px minus 1. Now we have the following equation that describes y, and then we have all those numbers. Now how can we maximize the use of this equation? So based on our support reactions, we can say that the maximum deflection occurs at x is equal to L over 2. So, okay, so maximum deflection, I need to put a note, maximum deflection occurs at x is equal to L over 2. What do we mean by maximum deflection? So let's say we have pin-ended connections. So you have your pin-ended connections here. Both are pins, and we discussed that this column will deflect like this. And you are certainly sure that your maximum deflection occurs at L divided by 2. Now, same thing for other connections. Note that initially we call it length. We have effective length. And now if we go back to our to other support reactions, so this is now your L, 0.7, the length of your beam. So your deflection right here happens at 1/2 of your LE, 1/2 of your LE. It's just in our case, we kind of assume that we have pin connections at both ends. So let's go back to next, go back to my screen right here. So now at maximum deflection L over 2, so we can use this L over 2 and substitute it to our equation. Now once we do those substitutions, we will get the following. So now we can call it as Y maximum, which means that's the maximum deflection we can get at this specific point. So Y max is equal to E times tangent small pl over 2 sine small pl over 2 plus cosine small pl over 2 minus 1, and that's the equation. We can further simplify the equation. So which means, so max is equal to E times sine squared. Okay, sine squared. So we can have this form as well. L over 2 plus cosine squared L over 2 divided by cosine P L over 2 minus 1. And we made this simplification in order for us to get this equation right here, which is now E is equal to secant of your P L over 2 minus 1. Now that we have our final form, so we have not final form, but we have this equation that relates the y max and then this L right here. Now we're not done yet because note that this is small p. And earlier we assumed that our small, so we go back here. Remember that we have this assumption that we have to put it back again to our equation. So now let's put it back to this simplified form of your y sub max. Okay, change this one. So recall small p squared is equal to p over e I, or we can also say that small p is equal to square root of p over e I. Now substitute it back right there. We're going to get y maximum is equal to E. Now we have our secant equation here. Square root of P over EI L over 2. And then we have minus 1. Okay, just checking if it's correct. So let's call it equation number 4. Now we have the following equations. Now the problem with this is if you're going to look at this equation, so say this guy right here. Now that value could be problematic because if you're going to, so note that your y max could reach infinity. In reality, it's infinity. It's a large number, but it's not infinity. But when this part of the equation P over EI L over 2 is equal to pi over 2. Take note that this is secant of this angle right here in radians, which means that this is your 90 degrees. So note that your cosine of your 90 degree is equal to 0. And your secant is the inverse of your 0, which means this quantity right here becomes infinity. But in reality, it does not necessarily go to infinity, but it becomes large to avoid it. Now, let's try to work on this equation and get some equation that would make much more sense. Don't worry, earlier we're going to summarize all the equations that would make sense for this topic. Now, taking this part of the equation, which is PCR, sorry, not P over EI L over 2 is equal to pi over 2. Now we can also call it as our critical force, and let's try to square this function right here. And take note that we don't want this value. This is a very large deflection. That's why we called it PCR. Now, once we square this number, we're going to get the following. PCR is equal to pi square EI all over L square. And then this is the same equation for your centric load, which we extracted inside our y max. And we can say that EI, so it's just substituting or transposing all the terms to the other side. So your EI is equal to PCR L square over pi square. Now we're going to use this EI right here and substitute it back to equation number 4. So we're just manipulating the equation in order for us to get a form which we can use in different problems. So once we substitute EI to our Y max, so we have Y max is equal to E. Now we have a secant equation right here, square root of P pi square, PCR L square times L over 2. We have minus 1. And this one easily cancels out. Your L, because that's L, becomes L, square root of L squared, that's L. And again, we just substituted the values of our EI right here. We took this EI here, and then this is going to be the form of your equation. Okay. Now we have this equation. Oops, I forgot the square bracket here. Now the final form for your Y max after this step is E times secant of your square root of P over PCR times pi. So now it's outside your square root over 2 minus 1. So now let's call this one as our equation 5. And note that we have P, we have PCR. What are those numbers? P, it's just the load that you defined. PCR, it's the critical load that you need in order to buckle your material. Now, this equation right here would be useful. So in the next slide, we're going to show you the equation that makes sense, or the equations that you're going to use to solve different problems. So right now, we are just deriving those equations. I'm showing you how those equations were derived, but eventually we're going to have an example. Now, we are now finished with the equation for our Y maximum in terms of your load and critical load. How about our force? Now, your sigma max is equal to P over A. What do we mean by P over A? So if we're going to draw our eccentric load right here, so initially we have this, right? And then what we did is we used force couple system in order for us to move that arrow right here. However, we have to add a moment, which means that if we're going to calculate for our maximum stress, so we have P divided by A, so that's going to be this P right here, and acting on this area of our column. So that's P over A. How about accounting for that moment? So just imagine your moment could also produce a force, and that force is, or not force, sorry, produces a stress. And that stress, as we discussed in previous lecture, is your moment, and let's call it maximum. The C, that's the radius of your section, and then we have our I, it's moment of inertia. Now, this is MC over I, and that's stress caused by our moment. Now, how can we get our maximum moment? Now, in this case, we have to, so our M max is actually equal to P times Y max plus MA, which is equal to, and take note your M sub A, so this guy right here, M sub A is equal to P times E. So as we discussed before, so your Py max plus Ma is equal to Py max plus E. So that's how we're going to get our maximum moment. So eventually we can substitute it back to our equation here. And another thing is your I. Your I is equal to area times r squared, and your r is your radius of gyration. So if we're going to substitute it back to our maximum stress, we will end up with the following equation. So P over A plus P times Y maximum, so that's the maximum deflection, plus E times C divided by A r squared. So we're going to get this equation right here. Now note that this is Y max, and that Y max is related to this Y max right here, which means we can still manipulate our equation to get a different form. So now, so let's recall Y max. Eventually, we're going to get this equation here. So your sigma maximum is equal to P over A. It's just the same right there. 1 plus E secant of square root of P over EI times L over 2 divided by r squared C, this one right here. And eventually we can again change the form of our equation, so we have the maximum is equal to P over A 1 plus EC over r squared, so we just remove those numbers there, secant of your pi over 2 times square root of P over PCR. And where did this come from? So which this part right here. So note that it comes from your EI again. If we look back our derivation, we have something about EI here. Oops, it's far away. Sorry, I think it should be somewhere here. I think it's in front here. So we have, okay, I think, yep, just looking, where's that EI that we wrote? Yeah, this one right here. So that's this one. So yeah. So we use that relationship in order to take this relationship right here. Now you can also rewrite the equation in different form. I'm just rewriting all the equation because, for example, this equation right here doesn't have your PCR. This one does have your PCR. So eventually you will realize which equations will make sense when you are dealing with a specific problem, which we're going to do, I think, in the next slide. So we can even rewrite this form as P over A, that's maximum stress, 1 plus EC over r squared, and that's a secant 1/2 square root of P over EA times, now let's call it effective length, LE over R. So that's another function here. Now in your exam, you're not going to derive equations. I am doing this one so that you know where those equation came from, so that you will not be okay. Yeah. So okay. So note here, sorry, yeah. Note here that your factor of safety. So I forgot one point right here. I just checked my notes. So factor of safety. Note if you're talking about factor of safety should be applied to the force and not stress. So that's a common mistake, but it should be applied in your force and not in your stress. Now, let's look at our example so that we can see how these equations work. So these are the most common equations that you're going to use for these types of problem. So you have this form which we derive, so P over EI L over 2. So we change our EI into this form, P over PCR minus 1. And then we have this equation as well, which we have our sigma maximum. We have another sigma maximum, and the only difference again is 1 contains the critical load, 1 does not contain the critical load, and then we also derive this P over A is equal to max divided by those quantities. Now, let's go to this example right here. So the uniform column AB consists of a 8-foot section of structural tubing with a cross section shown below or on the left. Using the Euler's formula and the factor of safety of 2, determine the allowable eccentric load for the column and the corresponding normal stress. So we are looking at, for problem A, we are looking at this point A right here. Now, assuming that the allowable load found in part A is applied at a point 0.75 inch from the geometric axis of the column, determine the horizontal deflection of the top of the column and the maximum normal stress in the column. Use E is equal to that value 29 times 10 raised to 6 psi. And you have all the numbers of your section. So you're going to see that A is equal to this number, I, radius of gyration, C, you have this dimensions right here. So you don't have to really calculate for your area. You're given with all those numbers right there. Now let's solve this problem. So first, let's analyze the column. Now the column has one fixed end. So your B is your fixed end. And then 1 is a free end. So, okay. So our column looks something like this. So that's your column. That's a fixed end. And let's say if you're going to apply a load, it will buckle like this. Which means for this specific problem, your LE, your effective length, is equal to 2L. And we can easily get those numbers. So that's 8 feet. So from point A to point B, that's 8 feet. So that's your L. So you can easily calculate your effective length by 2 times 8 feet. And then you're going to get 16 feet right here. And that's what we call our effective length. Now, from these numbers, we can also calculate our PCR. Now, what's the equation for PCR? So that's pi square EI divided by L sub E square. Now, as long as you have your LE, you have your E, you have your I, you can get PCR. So that's one hint that you can easily get your PCR. So in this case, your I is equal to, so if we're going to go back to the problem that's on the left, so that's I, 8 inches raised to 4. We have our E, which is stated in the problem, 29 times 10 raised to 6 psi. You have your effective length, which is 16 feet. And then we're going to solve this PCR right here. So for PCR, we have pi square. We have 29 times 10 raised to 6 psi. So we have 8 just to the 4. And twice the square of your effective length. And I'm going to convert it to inch because you have inch there and inch right there. So we're going to get 192 inch, and then we have to raise it to 2. Now, from here, we can get PCR is equal to 62.1 kips. So we have now PCR 62 kips, pounds. So now, let's move to the problem itself. So what we did is we just analyzed the column itself. We took whatever we can take. In this case, we took the effective length, the critical load, and now we're ready to start the problem. So for letter A, using the Euler's formula and the factor of safety of 2, determine allowable eccentric load for the column and the corresponding normal stress. So now, here we have factor of safety, which is equal to 2. Now, first thing that we have to do is we have to first find the allowable force. Again, we are asked for allowable force, let's call it PO, and then we are also looking for stress. Let's check the problem. Centric load and the corresponding normal stress. So allowable centric load, which we call P allowable, and the corresponding normal stress, so which we call sigma right there for letter A. Now for the allowable force, you have to multiply this by your factor of safety, and that's equivalent to your PCR. So remember that you are multiplying it to this load right here, not to your PCR. And you know your PCR, which is equivalent to 62.1 kips. So you can easily get your allowable load, which is equal to 31.1 kips. Now, how about the stress? Your stress is equal to P allowable divided by your area, and that's easily 31.1 kips. Now your area, it's given to your problem. So if you look on the right corner here, so your A is 3.54 inches square, so you just have to divide it by 3.54 inches square, and that will give you an answer of 8.79 KSI. So we solve letter A without any problem. So we have this guy right here and then this guy right here. Now that's easy because it's centric load. How about eccentric load? Now for the second problem, we have 0.79 inch. So your E is equal to 0.79 inch. So we move our P from this spot right here going to your centric position. So now let's first so for eccentric, let's first define all the numbers right here. So now we know that our P allowable is equal to 31.1 kips. Now, we're going to use this one because just imagine that if we have eccentric load, we're going to move this load right here to your centric one. So eventually you will have an eccentric type of loading. However, you have to add your moment, which is created by this E right here. So this allowable right here is kind of still valid, but so that's your allowable, but we later on we're going to add the effect of moment and so on. We're going to look at those equations later. So now we have P allowable, which is 31.1 kips. We have our PCR, which is equal to 62.1 kips. And then we have our E, which is 0.75 inch. And the question in B is find the deflection at A. So determine the horizontal deflection of the top of the column, which means the deflection of the top of the column, the deflection of this A caused by this P, and the maximum normal stress in the column. So we need to find deflection at A, and we are also interested with our sigma maximum. So that's our objective for B. Now, for deflection at A, imagine that we have a fixed end. We have our force. It could deflect this way. Change the color. So it could deflect this way. which means that if this is point A, your maximum deflection is actually at point A, which tells us that your y max is equal to your deflection at point A. And you know the equation there. So you're given with P and PCR, and you are given with the following equation. So E is equal to, y sub A is equal to E times secant of pi over 2 times square root of P over PCR minus 1. So we have this number right here. Now, based on this, P over PCR, we can easily say that this is 1/2. Based on the numbers on the top, so you can easily say that this is kind of 1/2. So this value right here, it's 1/2 or square root of 1/2. It's minus 1. Now, your y sub A is equal to 0.75. Your 0.75, that's your E, times secant of pi over 2 times square root of 1/2 minus 1. So we have this, and it's just putting all the numbers in your calculator, and then you will get y sub A is equal to 0.939 inch. And again, this 0.939 inch, it's this deflection right here. Again, this is free at on the top, and this is fixed support right here. And that's the deflection at A, and that's your Y max. So now we are now done with deflection at A. We're going to move to our sigma maximum. We have equation for our sigma maximum, which is sigma max is equal to P over A divided by 1 plus EC R square, secant of your pi over 2 square root of P over PCR, and we have something like this. Again, remember that we kind of derived that equation earlier. So, okay. And this guy right here is again square root of 1/2, which is based from that one. We have our P, which is just your P allowable right here. We calculated. We know the area. We know radius of gyration from the given. So if you look on the bottom on the right, so we have R 1.5. So we also have the C of our section, which is 2. And then we have E, which is 0.75. We know that one. So everything, all the numbers right here, we know. So let's substitute those numbers to our equation. So we have 31.1 kips divided by 3.54 inch square, 1 plus 0.75 inch, that's 2 inches, times 1.5, that's 1.5, that's an inch, okay, square, secant of your pi, divided by 2 square root of 2, so we have this. And now, based on this numbers right here, we're going to get sigma maximum, which is equal to 22.0 KSI. So now we solve our problem right here. So again, the questions for columns, it's not too difficult. I would say as long as you know how to use the formula, you should be fine. It's just moving those forces to this central axis in order for you to solve the problem, and accounting for the effect of, let's say, E right here. Okay, so I think that's all for the chapters and columns, it's a short chapter. So I'll see you again in the next lecture.